So first we'll go over what we did in this workshop. We were provided a background, and based on that background, we laid the network with catch basins, transition elements, and pipes. And notice that for our inlets, we set them to be 100% capture in sag inlets so that we didn't really have to say what type of inlet it is. This implies that they are at a depression on the road that basically will collect everything that falls onto it. So we really are not designing the inlets per se. We're going to be looking at inlets after this design and then see what that is all about. But right now we were simply designing the underground network, right? Um, so what we did is we input the location of our inlets, and we said again they're all in sag and they're going to collect everything that falls onto them. If we looked at the background, it had some contour elevations. We can see the bottom of the pond is at 494 feet, goes up to 500, and we have this little hill up here at 510, and then this other area, it's 508 and 506 feet. So that's just to give us an idea of what's going on. So we have to address the challenge of this hill being here, right? So what we said is we have our road, we put this network here, and if we look at the profiles, what we did is we have to serve these homes. You notice that the background shows lot 21, lot 20, lot 19, so we have to be able to get the water for all these homes. So we have two separate networks that we're running in this model. So we have from CB1 to outfall 1 and from CB4 to outfall 2. Okay, so let's take a look at the profiles. Well, so basically we input catchment information, right? Which we said we're going to use the rational method. We're going to have multiple sub areas, and we had 87% single family residency and 13% paved with its respective C coefficients. We defined the time of concentration for each catchment as well. So you can see those times. We input storm data, so our IDF curves for the 10-year event that we're using for this design. Okay, so based on that information, StormCAD calculated the flows. And in addition to the flows, we had input pipes, and we said we were going to have a catalog of pipes available for it to pick its in its design. So we're going to go to the concrete catalog and take a look at that. Basically, we had pipes anywhere from 8-inch all the way to 120-inch for the design, and we had input the Manning's coefficient. These were all concrete, circular concrete pipes. Okay, so I think initially we had them all, I think they were all 8 or 12 initially, and then we were asking the software to do a design. And how did we do that? We went to our alternatives, design alternative, and we said, okay, for our pipes, make sure the minimum cover is 2 feet and maximum 15 feet. You're going to see that because of that hill, some of them have a pretty high cover. And we also said that in particular for pipes 5 and 8, which let's find them here, they're basically the ones discharging to this pond. Because there's no road there or anything, we were going to allow 1 foot of cover. Okay, so that's what we said here. We set specific local pipe constraints, and we changed that to be 1 foot. All right. In addition to the cover constraints, we set minimum velocity of 2 feet per second, maximum 15, and minimum and maximum slope. So we'll see that in the design that StormCAD came up with, it tried to always provide the minimum cover so that we're saving money on excavation costs. And then from there, it looks at the minimum slope, all right? And makes sure that whatever flows are flowing through it because it knows the area, it knows how to stick to those velocity constraints. And for our nodes, we simply said match the crowns. Okay, and we were going to say that we allowed the design of structure elevation for all of our nodes, including the 2 outfalls. Okay, so outfall 2 and outfall 1. And that's it. That's what we decided. And we said, okay, we're going to design it so that this is a free outfall. Okay, so we went over here and we said in the design, we set the boundary condition type to be free outfall. So there are no restrictions of flow. Okay, and we did say that the ground elevation was going to be 500 feet here. We had ground elevation also right from those contours that I mentioned. All right, so that's all we input, and then we run our design, and this is what it came up with. So now let's take a look at those profiles. Let me show you. We'll first look at that one over there. Okay. So here you can see that it came up with a pretty gentle slope. Notice that here at the beginning we have 507.5 and then 505.5. So it is sticking to the minimum cover in that location. We do have that kind of a hill that he has to um, comply with those. But also at the end, if you notice, there's a 500 elevation, ground elevation, and the cover there is 1 foot. So again, it's trying to minimize that cover. And at these locations, because it's a hill, it could have gone a little closer to the surface, but then we would have had problems with the slope. So let's take a look at the slope for this pipe, which is called CO6. If I go over here, I'm just going to type slope here. So notice that the calculated slope is the minimum that we set. Okay, so it's set to 0.005. And then this one here also has the same minimum slope. Okay, so that's how it designed that. And let's take a look at the diameters now. I think it's called size. Yes, so 10-inch for CO6, 12-inch, and this one 12-inch. So that's a pretty nice design. If we take a look at our profile, they're all mild profiles. M2. I'm sorry. Okay. And in terms of the flow, we can see 2.2 cubic feet per second and all of those results. So it looks like it's a um, pretty nice design. Notice this field here, we talked about this a little bit yesterday. Depth divided by the rise, it's 68.3. So that's one way, 68.3% is one way to see the capacity on our pipes. So there is capacity. Let's keep that one there and we'll take a look at the others. 80% here and 73%. So that was a pretty neat design that it did for us. Now let's take a look at the other profile. Now we've seen a lot of the details, and oh, where'd it go? Here it is. My other screen. Okay, so again, this is a nice design. You can see that it has energy grade line that's slightly above. We didn't take a look at the velocities over there, but we can do that here. Search by velocity, 4 feet per second. That seems to be kind of the average, around 4 feet per second. And let's take a look again at the depth over rise. So 54% for CO5, 59, 60, 65, and 75. So pretty good capacity. Let's take a look at the slope now. So again, if I go back to that profile, I will show you what it did at the beginning. So we can see, if I make it even bigger, can read the scale a little better. So it goes, it's exactly 2 feet of cover here. And then it had to maintain that slope. You see that the slope is pretty constant. It's the minimum slope we requested. That's why the cover at the end is a little bit bigger. So here we see 500 is the ground elevation, but the crown of that pipe is at about 494.5. So we have over 5 feet of cover there. And that's again because we set that minimum slope. So if I pay attention to the slope here, 0.005, 0.005. So if you wanted to spend some more time and actually play with this file a little bit, you could go here and try to modify the minimum slope, and you'd probably come up with a different design. Okay. All right, so we were asked under free outfall conditions, so what we have right here, what profiles do we have? We can take a look at here the pipes in the flex tables. Let's see if I have it. Don't have that listed, but I can take it out. Okay. Profile description. Okay, so you can see that they're all mild slope because they're all M profile descriptions. So they're all pretty nice. They have that minimum 0.005, so it's good slopes. And this is what happens when we don't have water in the detention pond. But what happens when the detention pond is completely full? So at 499 feet, well, we run it and we were able to look at our profiles. The first profile, so this one over here, it's not that affected because that pipe is submerged. It's completely submerged, but the tailwater is 499 and it affects the first pipe, CO8. Now let's take a look at what happens with our other profile. 499 is right here. So you can see that the first pipe, the second pipe, and yeah, so basically our first 3 pipes are completely submerged. And because we have water coming in, as well as the backup from the pond, pretty much all our pipes are going to be submerged. So if we go back to that flex tables, conduit table, and take a look at the profile description, we can see that we have pressure in those pipes due to the water level of that detention pond. Okay. And finally, there was a question about, at this catch basin, what is the hydraulic grade line in? Easiest way to see that is select the element that you want, right-click, and do data table. And we're going to see for both scenarios that one catch basin hydraulic grade line in. So for the design, when the outfall is not submerged, it's about 500. But when it is submerged, we have almost a foot more in hydraulic grade line.
If you found this video helpful, please give it a like. If you want to see more such series, consider subscribing to our channel. Thank you, and see you next time.